Open any textbook on statistics, and you will find a specific date for the birth of mathematical probability, 1654. That year, Pierre de Fermat and Blaise Pascal exchanged letters solving a dispute known as the problem of points. But the mathematics of chance were solved 134 years earlier, in 1520. Girolamo Cardano was serving as the student rector at the University of Padua. During this time, he wrote Liber de Ludo Alle, or the Book on Games of Chance. For centuries, historians dismissed the text. Because Cardano was an inveterate gambler who included chapters on cheating and player psychology, academics categorized the work as a gambler's manual. The Latin manuscript contains a systematic formalization of the mathematical sample space and the calculation of expected value. Back in the 16th century, gambling outcomes were widely viewed as expressions of fortune, fate, or divine will. Cardano ignored superstition. He approached gambling as an empirical, physical system. He analyzed real-world variables, documenting how dishonest players manipulated the mechanics of a hanging dice box or pressured opposite faces of a die to alter its shape. He applied this same scrutiny to the asymmetric bone pieces used in ancient Greek games like knucklebones. Through this physical analysis, he realized that to master the behavior, by stripping away physical superstition, Cardano achieved the crucial step required for probability theory. He assumed an idealized model of reality where every possible outcome can be mapped and counted. Cardano coined a specific term for the total universe of possible outcomes. He called it the circuit. The simplest abstraction begins with a single honest die, which has a circuit of exactly 6. This grid represents the combinatorics of scaling the problem to the throwing of 2 dice. Cardano's first enumeration step was to isolate the 6 doublet throws, like 1-1 and 2-2. Next, he identified the pairs of unlike faces, counting exactly 15 unique combinations. He recognized that these unlike faces appear in 2 distinct orientations. A 1 and a 2 can fall as 1-2 or 2-1, doubling the 15 pairs to 30. By accurately mapping these 36 distinct permutations, Cardano successfully defined the sample space over a century before the term existed in mathematics. With the circuit defined, Cardano calculated specific odds by isolating favorable subsets of outcomes. This grid shows the 36 possible outcomes, allowing us to trace Cardano's calculation for throwing a sum of 10. He started by identifying the single doublet that sums to 10, 5-5. Then, he identified the unlike pair of 6 and 4, counting both of its orientations, 6-4 and 4-6, yielding a total of 3 favorable outcomes. Cardano stated his conclusion as an exact fraction, 3 out of 36, which simplifies to exactly 1/12 of the total circuit. From these fractions, he established the principle of fair wagers. He argued that a player's betting stakes must be strictly proportional to these exact odds. This formulation replaced gut instinct with expected value.
Cardano proved that a game is only fair when the financial payout matches the precise ratio of the sample space. This 3-dimensional cube maps how Cardano pushed his abstract model even further, scaling his logic to 3 dice. He defined the new total circuit size as 6 cubed, resulting in 216 possibilities. He then posed a complex question: what are the exact odds of throwing at least 1 ace across 3 dice? Manually counting every permutation containing 1, 2, or 3 aces across 216 outcomes is a massive cognitive burden without modern algebraic notation. Cardano devised an elegant workaround. Instead of counting the throws that contained an ace, he counted the throws that contained 0 aces. He was utilizing the concept we now call the complement rule. To find the complement, he calculated the permutations of rolling any of the other 5 faces across all 3 dice. 5 cubed yields exactly 125 outcomes containing no aces. For his final step, he subtracted this complement of 125 from the total circuit of 216, leaving exactly 91 favorable outcomes. Cardano was intuitively executing modern set theory logic to sidestep a brute force calculation problem. The final mathematical barrier Cardano breached was calculating the odds for successive independent events. He presented an extreme stress test in his manuscript, attempting to roll an ace, deuce, or trey on 2 dice 3 throws in a row.
This equation scales the base circuit. Cardano cubed the two-dice circuit of 36, yielding a total of 46,656 possible sequences. He applied the same exponent to his favorable subset. He determined a single throw had 27 favorable outcomes, and cubed it to find 19,683 favorable sequences. He subtracted the favorable sequences from the total circuit to find the remainder of unfavorable outcomes. This gave Cardano an astonishingly precise betting ratio for the sequence, 26,973 to 19,683. By correctly exponentiating both circuits and subsets, Cardano successfully modeled independent, identically distributed variables. In this single text, Cardano defined the sample space, utilized combinatorics, used the complement rule, and multiplied independent probabilities. He even articulated the law of large numbers. He acknowledged that while short-term variance exists in a few throws, over an infinite time frame, the mathematics of the circuit always assert themselves. If Cardano achieved all of this, why did Pascal and Fermat receive the historical credit? The answer is timing. Cardano wrote his manuscript in 1520, but it sat unpublished and unseen for over a century. It was finally published in 1663, 9 full years after Pascal and Fermat's letters had already circulated through the academic world. Pascal and Fermat's correspondence reached an audience Cardano never did, providing the direct momentum for modern probability theory. But the core logic, from the mapping of circuits to the calculation of independent variables, was established by Cardano over a century before the academic world took notice.